Hello, my name is Tommy Haraldsson and I work at the Department of Micro and Nanosystems at KTH, Royal Institute of Technology. And I would like to talk to you today about the research I lead into polymers for medical diagnostic devices. And one of the main reasons for doing research into medical diagnostic devices is the rise of multiresistant bacteria cases in Europe. And as you can see, in some countries, up to half of the cases reported of bacterial infections are actually caused by multiresistant bacteria. This is very bad because the diseases that you could cure 10 or 20 years ago are actually sometimes deadly or sometimes lead to very, very long hospitalization, which is of course very bad for the individual, but also very bad for society. So, how does this come about? Why is this on the rise, the multiresistant bacteria cases? Well, let's take an everyday example. You have a bit of a sore throat, happens to everyone. You wait for a few days, it doesn't get better. So you go to the doctor. The doctor will examine you and check blood pressure, etc. And it may also test your blood to see if there are any biomarkers, such as C-reactive protein, that will tell you whether it's a bacterial infection or not. And then he will take out his prescription book, he writes you a prescription for an antibiotic, and hopefully you get better. But the quality of this, of course, depends on the quality of the diagnosis. If you get the wrong diagnosis, you get the wrong antibiotic. So we need better diagnostic equipment. So let's take this middle piece of equipment here as an example. These diagnostic devices typically all have the same setup. They have an inexpensive reader because it needs to be in all doctors' offices at the point of care. And it also has a very cheap disposable cartridge where the actual patient sample goes. This disposable cartridge is typically made out of a polymer, very cheap polymer. And it's in this area that I conduct my research. I want to make these disposable cartridges much more smarter and more versatile. So let's look a bit at what an advanced diagnostic chip could look like. A chip that could actually perform multiple of disease detections at the same time. So here on the left hand side of the chip, you have whole blood. So the doctor pricks a finger, takes a little drop of blood. The blood is sucked automatically through capillary action to a plasma extraction chamber, where the red blood cells are taken out. The plasma then it goes over a biomarker detection site where molecules of interest get stuck in certain parts. And then you have suction chambers and they provide the constant pumping action of the chip. The chip is made of polymers still because polymers are the only feasible alternative. So let's look what the polymer needs to have in terms of properties to fulfill this. It needs to have minute channels and they need to be perfectly replicated from device to device, so the answer is always the same. It needs, of course, to have a transparent material so you can see the color lines that you use for detection. And it also needs to have very, very precisely controlled surface properties, which is very important for chip function since that provides the suction action in the chip, the pumping action. So all of this translates into demands on the polymers that you can use. So let's look at a small selection of the polymers available out there. So we have amorphous polymers and semicrystalline polymers. Semicrystalline polymers cannot be used because they are opaque, so you couldn't see the color change. So they go away. And then ultra polymers, they have really, really good mechanical properties, etc., but they are very difficult to mold. So they also have to go. And in this way you go on and you end up with only 3 polymers left that are used for all commercial microfluidic devices used today. And the industrial polymers are cyclic olefin copolymer, polystyrene, PMMA, or plexiglass as it's also called. And in research, we don't typically use those. We use PDMS or silicone rubber instead because it's much, much easier to work with. All of these have drawbacks. So the industrial polymers, there you need an injection molding machine, which of course is expensive. And these industrial polymers are thermoplastic, so they don't like solvents. And sometimes you want to use solvents in the processing of your chips. So that's a drawback. The research polymer is not really good for diagnostic devices because it actually swallows up lots of small molecules. And those are the very precise molecules that you want to detect for determining which disease you have. So we set out to make our own polymer that would answer up to the needs much, much better than the alternatives that we currently have. And this is the new dual cure polymer that we have developed up at MST. So before curing, it's a liquid, so it's a droplet. And then you put it into a mold where you have one mold half with a pattern on it. You pour in the polymer, pre-polymer, and then you put a lid on it. And then you cure it using UV light. So you shine light from the top. And what you take out from this mold then is a rubbery material which contains lots of epoxy groups. So you can say it has its own epoxy glue already stored in the material. Then we stack up all the different layers that we need to build the device, put it under pressure, put it in the oven, and then it cures to a very, very hard, transparent, nice polymer with really, really good bonding between the layers. And here you can see in the corner there that it is very flat and unwarped. So let's see how this answers up to the challenges that I put up before, the challenges for building a microfluidic device. So the minute channels need to be perfectly replicated, and micropatterning via molding works really, really, really well. There you can make very, very small channel sizes, and they replicate really well. And then, if you want to have a more speedy process, you typically would like to do photolithography. And in photolithography, you let the shadow mask define a pattern. So you have a bottom, you have your liquid, you put a mask on it, then you shine light, and whenever the light is blocked, you don't get a structure. And whenever the light comes through, you get a structure. So it's a very rapid way to prototype things. And here you can see that we still have very good replication of channels, and it's also very transparent. In the C picture, you see that we put a device on top of the KTH logo, and it's still, you can read it really well. And tuning of the surface chemistry is also very important to make sure that it has the right pull so that the blood is sucked at the right pace. And here we can see that it's very, very easy to surface modify. You can have a high contact angle. It's water that we put on two parts of the device. One is treated in one way and one is treated in another way. And there you can see that you can control the surface energy really, really well. And this is the very, very talented team that is responsible for all the pictures you have seen. And the future, what are we going to do in the future? The future challenges. Well, as always, going smaller is always interesting because you can pack much, much more functionality into any given area, which is equivalent to what's happening in the semiconductor industry. But it's not only that. When you go nanoscale, new phenomena becomes very, very apparent. So you can make surfaces that don't wet at all. You can put oil on it, or you can put water on it, and it still forms droplets that just roll off. It's very, very interesting. It's also a very feasible way to make antibacterial surfaces, so that bacteria that touch the surface just die. Another thing which is also very interesting is to expand on just modifying the surface energy of the material. And maybe we could incorporate conductive patterns, so you can actually make little electronic circuits directly on the chip. Or you can also bind directly bioreceptors into the chip, and that makes for very, very robust diagnostic devices. So with that, I would like to conclude my short talk of the research we do into new polymers, and I thank you for your attention.